Hello everyone, this is Sushmita Shaini. Welcome back to my channel. And today we are going to talk about one of the most important and frequently discussed topic in computer science and cybersecurity, which is buffer overflow. A vulnerability that talks very small at first but has the power to completely break a system if exploited correctly. So let us start from the basics in a very simple and clear way. In computer programming, a buffer is a temporary storage area in memory that is used to hold data while it is being processed, such as user input, file data, or network packets, and every buffer is created with a fixed size, meaning it can store only a limited amount of data. But the problem begins when a program does not check how much data is being written into this buffer. A buffer overflow occurs when more data is written into a buffer than it can hold, and this extra data does not just disappear. Instead, it spills over into adjacent memory locations, overwriting important information such as variables, control data, or even function written addresses. And this is where the real danger begins. Buffer overflow vulnerabilities mostly occur due to poor programming practices, especially in low level languages like C and C, where the programmer has direct access to memory, but the language itself does not automatically fix boundaries. So, if the programmer forgets to validate input or uses unsafe functions like guts or scanf without any size limits, the program becomes vulnerable. To understand how buffer overflow actually works internally, we need to understand how memory is organized in a running program, where memory is divided into segments such as code segment and data segment and heap, stack. Buffer overflow usually target either the stack or the heap. In a stack-based buffer overflow, the buffer is stored inside a function on the stack along with the local variables and the return addresses. And if an attacker provides carefully crafted input that exceeds the buffer size, the extra data can override the program address, which tells the program where to go after the function finishes. And by overwriting these return addresses, an attacker can redirect the program execution to malicious code, often called shell code, which can give the attacker complete control over the system. Next, heap-based buffer overflow attacks, on the other hand, occur in dynamically allocated memory, where overflowing one heap buffer can overwrite adjacent objects or metadata, leading to memory corruption and potentially code execution. And although heap overflows are more complex to exploit, they are still extremely dangerous. One of the reasons buffer overflow is considered so serious is because it can lead to remote code execution, meaning an attacker sitting anywhere in the world can send malicious input over a network and take control of a system without physical access. Historically, buffer overflow vulnerabilities have been responsible for the most cyber attacks, such as worm or code red worm and SQL slammer, which spread rapidly across the internet by exploiting buffer overflow bugs in widely used in software, bringing down servers, networks, and even entire regions of the internet. Even in modern times, buffer overflow related issues continue to appear, sometimes in different forms like buffer overread vulnerabilities, which can leak sensitive information such as passwords, encryption keys, and personal data from memory. The impact of a buffer overflow attack can range from simple program crashes to complete system compromise, data theft, malware installation, and privilege exploitation, which is why it is considered a critical situation in operating systems, embedded systems, web servers, and IoT devices. Despite being a decades old vulnerability, buffer overflow still exists today because legacy code is still in use. Performance critical applications still rely on lower level languages, and not all developers can strictly follow secure coding practices. To prevent buffer flow attacks, developers must validate all inputs, ensure proper bonds checking, avoid unsafe functions, and prefer safer alternatives, while modern systems also implement multiple layers of defense, such as which detects stack corruption, address space layout, randomization, which makes memory address unpredictable, and data execution prevention, which prevents execution of code from data regions of memory. In conclusion, thank you for watching the video and please like and subscribe the channel.